So now we will do the series stub matching case. Earlier we have seen the parallel where we are working on the admittance domain. Now we will do the series stub matching. So naturally when you have something to do in the series, we are going to use a Z Smith chart and we are going to talk about the impedance rather than the admittance. So the problem is mentioned over here. This is a transmission line of length L which is terminated in the load impedance ZL, which is not equal to Z0, which is the characteristic impedance of the transmission line. Okay, we need to put something in series to match it to 50 ohm, and that whatever we are putting that as a stub, series stub in series, we are going to place it as close as possible to the load impedance point. Okay, then only it minimizes the reflections which are happening on the transmission line. Again, one more important note, as we have said that in parallel connection, that we are going to move along constant gamma circle. Why? Because we do not add any loss, we do not add any resistors, we are not changing the value of gamma in the process. So let's begin in the similar manner what we have done it in the parallel case. So first step is obviously locating the impedance point. This is the value of the load impedance ZL, that is 0.3 plus 0.6J. So which is located over here. Next step is actually to draw the constant gamma circle. So you take this as a radial distance and draw the constant gamma circle. Now what constant gamma circle depicts? It is basically the locus of the points of different values of impedances, but gamma reflection coefficient remains same, and that is what is precisely happening over a transmission line. If you do not realize any stub connections or parallel or series over there, the value of gamma remains same whenever the loss factor is not changing. And we are considering a lossless transmission line, which means that the loss component is not changing, the gamma value has to remain same. And that's why precisely we are going to move along constant gamma circle to realize the impedance matching. Okay, so fine. So once you are located that, our always step will be moving towards the generator. Our always first step will be moving towards the generator, and you are going to move clockwise in the Smith chart to move towards the generator. Okay, so you start this as a reference point, you extend this line towards the peripheral on the Smith chart, okay, and then you will locate a point which is marked on the wavelength towards generator circle. I have identified that point. So the reference, okay, the reference point over here is basically 0.09 lambda. The reference point over there is my starting point is 0.09 lambda. From that I am going to move towards R1 circle, okay, towards R1 circle. So you are going to move along constant gamma circle and intersect R1 circle over there. Okay, remember in the process we are not changing gamma. Fine. So we have arrived at R1 circle. You can intersect at the bottom also. But as I told you earlier, to move over here you require additional length. So length L1, which is being mentioned over there, will increase. So that should not happen. Your length L1 should be as close as possible to the load point. Hence, we are going to intersect over there. So we have arrived at this location. At this location, what is the impedance now? After moving along constant gamma circle, it is 1 plus Jx. Remember, it is x now because we are talking about the impedance. So we have arrived at this point, it is 1 plus Jx, that is the impedance over there. Now that plus Jx component has to be negated to realize the matching equal to 1. Okay, so this is the impedance at this point without the presence of this stub, let it be open or short. Without the presence of this stub, the location, the impedance at point L1 from the load point is 1 plus Jx. So we need to do some modification over there so that net impedance over there is equal to 1, that is the characteristic impedance. And that's what precisely what we are going to do. We are going to use a stub connection over there. Using that stub connection, we are going to realize total impedance is equal to unity. So we will be putting stub over there. Now to calculate that length L2, what you need to do, you extend this line, okay, you read the line over here. So that is around 0.184, okay. The point where it intersect at the R1 circle is 0.184. So your length L2, sorry, your length L1 is equal to 184 minus 0.09. Okay, so your length L1 is 0.184 minus 0.09. That comes out to be 0.094 lambda. That comes out to be 0.094. So L1 is basically 0.094 lambda. Remember, everything is in lambda. So we are doing impedance matching which is frequency specific. At other frequency point, that length differs. So that is not really the point where the impedance matching is being realized, or that particular impedance of 1 plus jx or 1 minus jx is obtained. Okay, so this is the location of the stub where we are going to put over here. Now let's find out the length of the stub. Now let's find out the length of the stub. So what you will do, you first take that imaginary part and mark it over. What is the imaginary part you require? Is the impedance over here is 1 plus 1.8j. So you mark minus 1.8j over here. You mark minus 1.8j impedance onto the R0 circle. Remember, you are going to mark this 1.8j on the R0 circle and locate the distance over here. That locate the distance on the wavelength towards the generator. So that distance comes out to be 0.331. Now you are going to realize the open circuit and series short circuit stub. So either it will be an open here, that is ZOC, or it will be short here, that is ZSC. And then in that process, because this is either a short circuit condition or an open circuit condition, and then you will realize and then you will move towards this point. In the process, you are required to realize the impedance of minus 1.8j. Okay, you are in that process, you are going to realize the impedance of that open or short circuit line as minus 1.8j. So where we are moving? We are moving towards the generator. We are moving towards the generator. So let's find out ZOC length. ZOC means what? Open circuit. You are in the impedance Smith chart now. Okay, we are not working on the admittance now. In the impedance Smith chart, where the open circuit or maximum impedance reside, this is my Vmax. So naturally, my Zmax is over here. So my open circuit, rather stub, will be calculated in length from this point. So the length of the open circuit stub will be 0.331 minus 0.25. That is my ZOC stub length. Okay, that difference you find out, that is your open circuit stub length. If I want to find out the short circuit stub, naturally this is my V min or Z minimum. So I have to move from this point and then I will move along this. My ZSC stub length will be 0.331. My ZSC stub length will be 0.331. So these are the values of the stub length which are obtained using series stub matching case. Earlier we have done parallel stub matching case, and when you put that length stub at this position, the net impedance which is offered at that point is equal to 1. That realizes the impedance matching. Okay, so this is all about series stub matching. Now in the next lecture, we will now talk about the other methodologies of matching, the impedance matching, that is the lumped element matching using LC section. Thank you.